Hi, and welcome to Software Design and Development Testing, Black Box and White Box Testing, Lesson 1. So, firstly we have to do a comparison of solution with the design specifications. When we design our software, we should be writing design specifications, and this takes place in the defining the problem stage. These specifications should be really specific, and they should be written as performance criteria. That way, when we go to look at them after when we test, we can see that our program does what it's meant to. When we're writing these criteria, the use of SMART criteria is a good idea. So SMART stands for specific, which specifies that the criteria mentions exactly what must be done. To make something more specific, we get rid of ambiguous statements such as the data is sent to the backup file and user is asked for input. Which data is sent? Which backup module? Which input is the user asked for? Things like these aren't very specific and so need to be made more so. M stands for measurable, and it looks at the criteria that must be able to be measured. Every criteria needs to be measured. If it can't be measured, we can't see if it does its job as much as it needs to. So things like most, some, etc., they need to be actually defined with a number or a percentage. So is most 9 out of 10 times? Is it 8 out of 10 times? By not clarifying these, you have a potential miscommunication between the client and the developer. You need to make sure you clarify these and specify numbers so that there can be no arguments when it comes to testing time. A, achievable. Criteria should be achievable. You can't use criteria that's not possible. Similarly, it should also be realistic. R stands for realistic. And you need to make sure that it is realistic. So things like guaranteeing internet access times is not realistic because there's variance of hardware and software across the system. If you state the possible speeds that are allowed and uptime percentages, they might be possible and realistic, but you can't say that, oh, we guarantee you'll always get this speed. Also needs to be timely. So what time frame does the criteria need to be achieved in? Okay, so maybe for page loading times, you might say it needs to load in 2 seconds. You might say that your project needs to be developed in 6 months, something like that. Each goal or each criteria needs to have a time on it. So yeah, these criteria form the basis of testing. You need to make sure that you have criteria outlined that tell you if you have a successful product. You test against those criteria, and if you fail the tests, you fix the problems. There are limits to testing, however. Okay, when you're testing in-house before installing it on the client systems, the possible testing you can do is limited. So it is impossible to test for every single possible occurrence of incorrect user input. You can test for the main ones or the ones you can think about, but users are very crafty and they will potentially always find ways to break your problem. You can test for the most common hardware setup in a business, but computers being built the way they are, you can't test every possible component because components change throughout their lifespan. You might find even with identical systems, the manufacturer uses a slightly different part, and software keeps getting updated as you go as well. So it's not possible to test for every single possible occurrence. You might find that there's things out of your control. So for instance, a key command that's in your system might be intercepted by the operating system or a piece of hardware and affect functionality. These things obviously can be patched later on, and they can be fixed when you install them on the client systems, but they're not things that necessarily can always be removed through testing in-house. If modules are small, testing every possible combination is possible, but as modules become more complex, this gets less possible. So programmers then focus on testing to find anticipated problems and not necessarily to test every single possible combination. If you want to make sure your program has as little errors as possible, you need to make sure to keep your modules small. So white box testing is testing the internal workings of a module. It is called white box as the programmer can see everything inside the module and considers the workings of the module. The main forms of white box testing are statement coverage testing, decision condition coverage testing, multiple decision condition coverage testing, and exhaustive decision condition coverage testing. Quite a mouthful. Statement coverage testing makes certain that each statement in the program is tested at least once. Okay, test data is generated so that all statements are executed. meaning that conditions need to have different values to execute loops or to run through both parts of an if statement. Okay, not every combination of condition is tested, only conditions that need to be tested to ensure that each statement is run. An example is following. We can see here that we have a section of code on the left, okay, and we have our test data sets on the right. The green refers to things that are true in this test, and the yellow refers to things that are executed in this test. So we can see in this data set, we are executing all three sections of code. We are just not executing code section 4. Moving on. Now we're testing condition A is true again. We're failing condition B. Over here we're failing condition B, and this executes code section 4. So over here we can see that code section 1, 2, and 3 were passed before. Code section 4 has been passed now. So all states are tested, but not all conditions. We didn't check if condition A, we didn't check what happens when condition A is false, condition C is false, condition D is false, condition E is false. The next one, decision condition coverage testing. This covers every statement, just like before, but in addition, each decision is tested with true or false values. So we need some more data sets for this one. Okay, data set 1 is as before, all conditions A, B, C, D, E are true, and we get the same result as before. Okay, moving on, we use data set B and we get the same thing. We've tested one false here. Data set 3, we test condition A is false, nothing else gets executed. Test 4, we test that condition C is false. Set 5, we test condition D and E is false. Okay, so in this instance, all conditions have been checked with true or false. However, not every combination of true or false has been checked. In multiple decision condition coverage testing, we test all possible conditions within decisions. Okay, so we use the same test as we did before, but we add 2 more. Okay, we make sure that we have testing condition D false and condition E true. Okay, and then we also test condition D true and condition E false. This, however, does not test every possible combination of conditions. So looking back at the last algorithm, in every test so far, these have either both been true or both been false. What we're doing now is we're going to test this one to be true and this one to be false, and then this one to be false and this one to be true. So the last form of testing is exhaustive condition decision condition coverage testing, and it's the ultimate form of testing. We test every single possible combination of condition for true or false. So for our program, there are 5 conditions, and there are 2 possible values for each condition, so that would be 2 to the 5 or 32 different possible combinations. As this tests everything, it is the most desired test. However, as programs get bigger, this gets harder. If we add one more condition, we double the number of possible combinations to 64, and therefore the number of tests that we need to run. So it's really, really, really important we keep the module small. Okay, here is the list of tests. As you can see, there's 32 tests and all the different combinations of false and true that we have. So it's quite large to test this amount of data. Black box testing. Okay, black box testing is called black box testing because we don't know what's in the box, or we don't care what's in the box. We don't consider it. In this set of tests, we test around the module. We feed the inputs in, we ignore the processing, and we look at the outputs. And by looking at the outputs, we can see if there's an issue, and if there's an issue, then we can go do some white box testing to find what that issue is. Alright, the 2 forms of black box testing here are boundary analysis and equivalence partitioning. In boundary analysis, it's when you use test data to check around the boundaries. So here's an example here where we use a case statement to give you grades. You can see over here, case where mark is greater than or equal to 85, you get an A, 70, you get a B, 55, you get a C, 40, you get a D. If it's greater than 1 or equal to 1, you get an E, otherwise you get ND, not demonstrated. Okay, so to test each of these boundaries, over here we test 86, 85, and 84. So we test one above the boundary, or more above the boundary if you want to. We test 85, which is the boundary. You test on the boundary, and you test less than the boundary. So in this case, 1 below 84. You could test lower if you want to. And we do that for each one. Okay, so we're testing each possible value above the boundary, on the boundary, and below the boundary. And that way we can see if the boundary is working as it should. Equivalence partitioning is when you generate 2 sets of data, one that should pass and one should fail. and you test both sets. So this is not just two values, this is two whole sets of data. So you might test 10 different values for each of them, and you check that they all pass or they all fail. So for our previous problem, we can test data for any integer from 1 to 100, and that should be data that passes. Okay, data that could fail, it depends on how you implement the algorithm, but it could be fractional numbers if you're using integers. It could be negative numbers if you've got a boundary that does that. It could be numbers greater than 100. Letters and symbols will also fail, okay, depending on how you've used variables. So it's really important to see that these do. If they don't fail when they should, that indicates that we've got a problem. If they pass when they shouldn't, that indicates that we also have a problem.